Hi, I'm Nick Fleece from Missouri State University, as you just set up here. So my talk today here talking about teaching group theory through puzzles. And so the whole kind of goal of this is just gamifying some of the methods that we can use to teach our upper division mathematics here. Gamification, probably a term that you've seen there, just using game design elements in non-game contexts. There's been a lot of different studies that have shown the effectiveness of this in teaching here. There's one study that I have here where they showed it improving the attitudes of undergraduate and medical science situation with statistics there. And so my background being working in group theory and abstract algebra is, okay, how can I try to gamify topics such as these? So in order to do this, first here I'm going to talk about the type of puzzle that you might have heard of, Calcudoku. But if not, here's a quick one so that we can understand how it works here. All right, so it's a Latin square that we have to construct. Be using numbers 1, 2, and 3 here. So every row has some permutation of 1, 2, and 3. Every column has some permutation of 1, 2, and 3. And then you have these cells, or where these all go here, and then, let's see, it's a little dull, but each cage here will have a clue. So like that 3 means that everything inside of this cage needs to add to 3, and so on. So if we kind of work on filling this in, well, first off, that center one is pretty easy. It's got to add to 2, and it's only got 1 cell in there, all right? So we got to put a 2 in there. So then we can start thinking about the requirement of this being a Latin square. And so in that second column there, got to have a 1 in one of those positions and a 3 in another position. But if we think about the fact that that cage right here needs to add to 3, if a 3 was right here, nothing else could go in there. So that tells us that we know that we're going to have a 1 in that position up there, and then we can fill in the rest of that cage so that it adds to 3. We can then just start working through this like any Latin square. I know there's going to have to be a 3 in that top left and in that middle bottom there. Let's see, that top left cage adds to 4. The bottom left cage there adds to 5, so we can add those in and then fill in the rest of the Latin square when we've solved our Calcudoku. Okay. So I had the idea of utilizing this, but with group elements, because we were only using one operation to fill in the cages. And a group is just equipped with one binary operation. And so I started working on this, and then as many things go, then you find a book that was published that same year that did the exact same thing. But so here we go. So David Nassim did this first here, introduced Calcudoku in his book, the Group Theory Puzzle Book. Super fun book, a fantastic introduction to group theory. It kind of walks you through group theory, teaching you through these sort of Calcudoku things. It's a really good book, highly recommend it. And so again, we have a Latin square with, right? We got a Latin square with the elements being the elements of the group is our goal here. Now a group, if you recall, isn't necessarily commutative. So now the order that we're going to do the multiplication in is going to be relevant. So I'm adopting the convention that we're just going to do it in Western reading order, so left to right, top to bottom. Nassim does it slightly differently, but you can check out that book there. And so let's take a look at this group doku and see how it can sort of teach us the ways of utilizing operations here in a group. So this is in C2 squared. This is the Klein 4 group. So it's a direct product of a cyclic group of order 2 with another cyclic group of order 2. So I have the presentation that's right here. So it's generated by x and y. X and y are of order 2, so when we square them both we get 1, and then they commute with each other. Okay. And so we'll get just 4 elements. We get x, y, 1, and then the product of x and y is a unique element there. So we have ourselves a group doku puzzle, which by the way, it's also not a name David Nassim used. I made that up kind of while I was writing. I think it makes sense. Anyway. So our group Doku puzzle, you can see, and some of the cages don't have a clue, so what's inside of those cages don't necessarily need to add to anything. We'll probably just be using the Latin squares to be able to solve this. So we get a couple of the freebies there. In row 1, column 3, we got a single cage cell. In row 3, column 4, we got a single cage cell, so we can fill those in. All right, and now we got to do a little bit of thinking. So what we can look at are these cages here that have Y's in them. We got this one here, and this one here. So these are going to be the product of two elements in the group, giving us a Y. Now for this to happen, they're going to have a Y in there somewhere. Okay? So that could come from either, we could take XY and multiply it by X, that would cancel out the X and we'd be left with Y. Okay? So XY times X is one combination that would work to fill that cage with a Y. And then Y times 1. Okay? Those would be our two options, but since we started with this XY right here, I know there can't be an XY inside of that cage at all. I know there can't be one inside of that cage at all. So it's going to have to be Y and 1, and so I'm going to need Y and 1 in this top right cage here, and then considering there's a 1 right here, I think I know just where I'm going to need to put them. Okay. Now, we also, so you can see the next thing I did here was filling in these X's, because if I know that these are Y's and 1's, Y and 1, not necessarily knowing the order, I know that this third row is going to still need that X, and this fourth column is going to need that X, right? These are Y and 1's. We haven't figured out the order just yet, okay? And then in this cage right here, so I fill this in with XY because what would I need to multiply X by to make the product Y? Okay, well I'm going to have to cancel out that X, add in that Y there, okay? And then we can fill in that top right cage like I was saying there. Let's see, that third column is almost completely filled, so we can just fill that in utilizing the requirement that it's a Latin square. And so we can start to see what all the group elements are if this isn't something you're too familiar with, right? Again, we got 1, we got our two generators, X and Y, and then the product of those two. All right, so now let's see what else we can do here. We know we got a 1 and a Y here, so we need X and XY somewhere up here. Similarly, we're going to have a Y and X in these two cells here. So let's investigate that top row here first. If we look at this top row, so it has to have X and XY in it. All right. So we got X and XY. Now we're going to have to multiply that cell, and that cell, and give us XY as our product. Okay? So I got XY and X. I don't know the order that they're in, but I know that these two are in there. When we multiply those, we get Y. Okay? So if the product of these is Y, and I need the product of the entire cage to be XY, that's got to be an X right there. So we can fill that in. All right, so we can fill that in with an X. Then we can do just some Latin square stuff. We know in that second row, we still need a Y, so we'll be able to add that in. And then there's only one place that an X can go in the remainder of this location. There. And then we fill in the rest of that Latin square there. Now that we have that Y there, we know in that Y cage on the left, it needed a 1 and a Y. We know the order those are going to have to go in and finish the Latin square. All right, so we've done our group Doku here. Okay. So, I think that this is an excellent way that to help students be able to learn sort of the ins and outs of how to do operations within certain groups. And so you can do these also in non-abelian groups, so when it's not commutative, makes it a lot trickier. And the smallest non-abelian group is order 6, so it'd have to be a 6 by 6 for it to happen, which I think just maybe take a little bit too long for this here to work through solving one of those. But you can certainly do these with larger and larger groups. All right. And again, I highly recommend David Nassim's book. Has tons of puzzles all the way up to some groups of order 10, some really big ones that are a lot of fun to solve. I was taking a lot of photos of that book and then doing them on the plane on my iPad there. That was a good time to do a lot of fun. All right, so let's talk about another topic that I wanted to talk about. So still in the realm of puzzles, okay? We're kind of differing a little bit, but another way that we can think about groups here. And so we're going to start with the motivation for this idea here is Pascal's triangle, okay? I think we've all seen this at some point, okay? All right, so we got Pascal's triangle. And so what I was thinking was, well, can we do something similar to this with groups, okay? So, Pascal's triangle, we got ones all along the edges there, and then the two things above add to get us what's below. So, all right, here's Pascal's triangle on the free group of one generator. So this is just a group generated by a single element x. So I put x all along there. And so I was looking at this and I'm like, well, this isn't really that interesting. It's just Pascal's triangle and the exponents now. Okay, so that's not too fun. So what I had the idea was to flip the requirement of Pascal's triangle. We had it where you multiply the two elements above, you add the two elements above, multiply in terms of the group is what I mean, so the group operation. So you do the group operation of the two things above and then get whatever is below, okay? So I'm gonna flip that there, and we're gonna create triangles where the requirement is the product of the two elements below gives us the element above. Okay? And so here is what we call an N triangle inside of a group. Okay? So what I'm doing is we need to create this structure utilizing the elements of a group. All right, and so you multiply, so G10 times G11 is going to give me G00, and so on. Okay. And then what this can become is see how big of a triangle you can make inside of a particular group before repeating elements. Okay, so you want to make it all with distinct elements. And so let's try one here. So I'm going to work on constructing a three triangle in Q8. All right. So Q8, this is the quaternion group, or at least the first one that we have there. So here's a presentation of the quaternion group, if you aren't familiar here. All right, it's generated by -1 I, j, k. You can do the quaternions with just two generators, but this is a more well-known presentation of the group here. Okay. And so, all right, I squared is -1, but then so is j, so is k. And then you multiply them, so just to help you recall here, so I times j will give you k, j times k will give you I, k times I will give you j. If you flip those, then it's going to negate those products there. And so let's try and construct a triangle in here. So it seems natural to try to put 1 at the top of this triangle. Okay. Why not? All right. So let's see. We got to get something that multiplies to 1. All right. I know -1 times -1 would give me 1, but we can't have any duplicates. Okay. And so there's the first thing that you start to see with these types of puzzles is involutions cause a lot of issues when you're looking for non-duplicates. Even if we go back all the way back here, okay. Now I didn't have any cages in this that are multiplied to a 1, but supposing that was a 1 there, this would actually be impossible, okay? Because the only two elements that can multiply to 1 are an element in itself, and we can't have duplicates within a row or within a column. Okay? So involutions become really important when we're looking at group puzzles like this. And so I know I can't have any involutions underneath there, so we can utilize other elements that have a distinct inverse. All right, so We'll just start at I here. I times minus I will give us 1. All right, so I need to multiply to I on the left here, so I'm going to have to add 2 elements down here. Okay. Well, let's see, j times k would give me I. But then we could start to think, all right, if I were to put j and k there, what would need to go in that third one to give me minus I? Well, it would be j again. And that's not going to work here. We're going to negate them both, do something like this. So yeah, minus j times minus k is I. But then, yeah, it's got to be minus j in that bottom left. All right, looks like this idea didn't work. Okay, let's go back. Let's restart. 1 didn't work in that top. Let's try I. Okay, so we're just kind of investigating here. Okay. Of course, I made this before, so I'm not fully investigating. But all right, so let's see. Does I work here? So what's a natural thing that multiplies to I? Just the j and k. Okay. And now let's think here. I need to multiply to j. Okay. So we got k and I, but we've already used both of those. Okay. But we could negate both of them there. Oh, that is a mistake here. Hang on. What in the world? Uh-oh. Where am I at? Okay. Yeah, that I in the bottom left just should be negated there. That's all. Okay, sorry about that. So, yeah, that should be a minus I. All right. And then we just need to put a -1 there. Okay. Again, imagining that it's a minus I there in the bottom left. And boom, we have ourselves a 3 triangle Q8. And so what we can say is that Q8 is 3 triangular. That's what we call that there. Now, could we make it 4 triangular? No, there's not enough elements in here. Q8, it's got 8 elements here. We need to have 10 distinct elements. So this is as triangular as you could make it, essentially. All right, and so I kind of fully defined that there, where we can define a group's triangle number, the largest triangle that we were able to construct, and essentially is as large as it would be possible a priori, just looking at the elements of the group. Then we say that it's fully triangular. And so we get some nice little theorems that we can start to think about. First off is that if the identity is going to appear in the triangle, it's got to be at the top. It can't be anywhere else. Okay? If we kind of go back and we were to imagine what would happen in a triangle if we were to, let me go back a little farther. All right, so I don't know, say G11. Come on. All right, so say G11, say this was the identity. Okay, that would force these two to be the same. Because this times 1 would have to be that. And so if the identity is going to be in there, it's got to be at the top. And then we also get that as long as a group has at least 3 elements, it's going to be 2 triangular. Okay? All groups. So everything except for the trivial group and the cyclic group of order 2, everything else is 2 triangular. Right? You can see that you just take, there's 2 different situations. As long as you have some elements that aren't involutions, okay? You just take an element, multiply it by its inverse, and you get 1 above it there. Okay? If everything except for the identity is an involution, then you just take 2 distinct involutions and multiply them together. And then you'll always be able to make a 2 triangle inside of that group. Okay? And so we got some constructions here of some 3 triangles in other groups. All right, so here's a triangle in C6. Okay? So this is just the cyclic group of order 6 generated by x. So x to the 6th is equal to the identity. You could also just look at the exponents here and think of it as doing the integers modulo 6. Okay, it's the same thing. The other group of order 6 is not 3 triangular. Okay, and the reason I'm starting at 6, by the way, right, if I want to make a 3 triangle, it's got to have at least 6 elements. S3 is not, take a little too long to walk through the proof of that, but we just kind of pretty much prove by exhaustion, show that it's impossible to do that. Now, what's interesting is you can do it in C6, but it's actually also impossible in C7. Okay? Which you would think, the larger it gets, the more elements that you have, it should be a little bit easier, because now I don't have to use all of the elements. You got one out there. But it's actually impossible to do it in C7, but you can do it in C8 and above. And so here's a construction that you can utilize in any cyclic group of order n when n is 8 or larger. You can see this won't work in C7 because x to the fourth and x to the minus 3 would be the same in that instance. And so what I'm starting to do, right, we've hit cyclic groups of order 8 now. Right? That's going to knock out a whole lot of groups, because if a group has a subgroup that exhibits a 3 triangle, then we can just exhibit that. All right. So what we're going to do is we're going to characterize 3 triangular abelian groups here, as where this is heading. Right? So we just need to hit a few more cases. Here's C4 cross C2. All right. I didn't write out the full presentation, but it's just following the order of the factors that I have written here. So x is the element of order 4, y is the element of order 2 there. So here we have one in C4 cross C2. Here's C2 cubed. All right, then we need C3 squared, a triangle there, and in C5 squared. All right, a few more cases. So I'm just kind of showing the cases that are all needed to combine into this characterization here. So C7 squared, and then we got Z, the integers. Too hard to do one of those there. And so here we have a finally generated abelian group is 3 triangular if and only if it's C6 or it has 8 or more elements. Okay? And then every abelian group after that. So looking at the proof here, right, if n's less than 6, it doesn't have enough elements. We already showed that C6 is 3 triangular, C7 is not. Okay? So that's every abelian group from order 1 to 7 covered there. Now, if it's going to have 8 or more elements, then we can look here. So an infinite finally generated abelian group is going to have the integers as a subgroup. That's from the fundamental theorem of finally generated abelian groups. Okay, probably my favorite. Put that in the top 5 of theorems, I'd say. I don't know. Love it. Anyway. And so we have that. If it's cyclic, we already know that it's 3 triangular. If we got a prime larger than 7 that divides it, then any prime divisor of a group, there's going to be a subgroup of that order by Cauchy's theorem. And so if you got one bigger than 7, that, starting at 11 here, that'd be C11 as a subgroup, which we just showed was 3 triangular as well. So we just need it to be, let's restart that sentence there. So now we got to account for when the order of the group is just a product of powers of primes 2, 3, 5, and 7. So if we got 2 distinct primes appearing in the factorization, then the direct product of the cyclic groups generated by elements of that order are also going to be a subgroup. That's combining Cauchy's theorem with like the Chinese remainder theorem, is what you need to show that. And then those would be large enough. And then finally, if G itself is a P group, then we got our 2 group. So if it's a 2 group, we showed some of those cases, and then it's basically all the previous triangular cases, so you can look through there. And then should the time, I'll jump ahead here. And then, one more thing I wanted to show you. So this is when a group is omega naught triangular. Okay, so what we're doing is we're trying to make an infinite triangle inside of these groups. Of course, we're going to have an infinite group in order to do this. Okay. And so what I was able to construct is a way to do an infinite triangle in Z that will keep satisfying this. So I have the first 4 rows created here. Okay. So you start with 0 here and -1 here, and then you have the requirements of the triangles that the 2 elements below an element add, in this case, to what's above. So that would force a 1 to be there. And then what you do each time you get to a new row is where did my thing go? All right, so we're just adding 1 to whatever this element is, putting it over there, and then we just gotta alternate the signs along there. And if you do that, you can create an infinite triangle. There'll be no duplicates because the magnitude of each of these numbers is increasing each time.
But can you get all the integers?
This will not get all the integers. It'd be fun if we could get all the integers. Okay. Certainly something I've investigated a little bit to see some other ways, but at least this gives us an omega not trying. References. Thank you all for listening.